Well, good morning, good afternoon, or good evening, depending on when you're watching this, calculus students. Today's a really, really important talk on the chain rule. One of the most important topics we'll cover because it keeps coming up over and over and over again throughout your calculus career. So, as usual, my talk about the chain rules will start out with a little story. And as usual, my story will relate to a Volkswagen. So on the Volkswagen, so I've converted my VW van to a 1.9. So it's a VW Euro van conversion. So I converted it to the 1.9 turbo diesel. So I've got a full-size van in which I can get 32 miles to the gallon. But that's not enough for me. So I decided to install a blender. But the way I did it is this. This is the flywheel, which is really connected to the engine. And there is the flywheel here, radius equals 10 centimeters. It's not actually the flywheel, it's kind of like a belt wheel that is fused onto the flywheel. But anyway, the radius here is 10 centimeters. All right. Now it's important to note that on this particular wheel, part of the timing light or the timing system is a white letter X, right? That's drawn there. Now that connects to the another wheel down here, smaller wheel. That's for the AC unit, the AC compressor, and but in German, the word for air conditioning is Unterklimaanlagen. So I'm not going to write that out every time, so I'm just going to call this U. So the pulley for the AC unit, and this has a radius of 5 centimeters. All right. Now, what does this have to do with my blender? Well, my air conditioning isn't actually connected. So instead of having my air conditioning, it's connected via a belt. Oh, and this belt here, let's draw this in blue. There's a blue belt that connects these two pulleys, and it goes around here like this. And this pulley goes up here like this. Da, 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 da. And by the German Bosch belt manufacturing standards, this belt is called F. It's an F-sized belt, right? But I don't have the compressor. I don't have all that stuff hooked up yet. So instead, I decided I'm going to add a blender, right? And so my blender is going to go up here. So it's a blender driven by the engine, and it has another pulley, and the radius here is what that work out to be 2 centimeters, right? And then there's a pulley, another belt that connects these two pulleys, like that, like that. And by again, the Bosch German belt sizing thing, this is called a size G belt. They letter all their belts, all right? So how does this thing work? The engine X drives this pulley for the air conditioner, but the air conditioner isn't hooked up, so I've got another belt that goes from the air conditioner pulley back to my blender. I'm going to call this particular pulley, let's call it Y, because why would you not want to have a blender hooked up in your Volkswagen van? All right, now the X drives U, and then U drives Y. So it's always a good idea to label our variables. So let's label these, the air conditioning related variables in blue, right? Where U is, that should be a U. That looks a little bit like an A, so let's erase that down here. That should be the letter. U is turns of AC, and then X equals turns of engine. All right. And then over here in red, we'll label some other variables. In this case, y is what I'm really interested in. Y equals turns of blender. And, well, I guess that's attached to u, so u shows up a couple times here. U, and to be consistent, that better be turns of the AC. Okay, good. Now, if I'm looking again at the air conditioning side of this thing, before it gets to the blender, I know that the U is going to be related, I mean, the number of turns that this thing makes is going to be related to the number of turns that this thing makes. So U is going to be some function of X, right? And in fact, I know what it's going to be. U is going to be 2 times X. Why do I know it's 2 times X? Because the radius is twice as big. So every 1 time this goes around 2 times. Oh wait, for every one of these, this does 2. Oh yeah, that's the derivative. So du dx equals 2, right? Yeah, sure it is. And then we go over here on the red side of things. I know that, well, y is what I'm really interested in. So y is going to be some function of u, right? And that's a g belt that connects it. So I'm going to call that a y equals g of u. And I also happen to know what that is, since this is 2 and that's 5, so that's 2.5 times. So y is going to be 2.5 u. Right, so for every one rotation of this one, right, because this one is really driving this one is going to be 2.5 times, right? Yeah, this turn goes around one side, so that's, oh yeah, so that's a derivative too. So dy du, right? The rate at which this turns relative to this, right? The rate that this changes relative to this is 2.5. Yeah, so I guess I could have done that a couple different ways. First of all, I know the function, right? And I can just take the derivative of this function. It's 2. That makes sense. Alternatively, I could have, I can see that this will spin twice as fast as this one, so du dx is 2. Okay, fine. And the same thing applies over here. But there's one little problem, and that problem is my dashboard doesn't tell me how fast the blender, because that's an aftermarket thing, or the AC are spinning. Right? If I want to know how fast my blender is going, how do I figure this out? Well, if I look at it this way, y is a function of u, right? Ultimately, I'm interested in my blender, right? So y equals g of u. But u is a function of x, right? U equals some function of x, right? So that means that y equals g of f of x, right? So this is a composite function. This is a composite function here, or a function inside another function. So there's a function inside of a function. F is the inner function, g is the outer function. So f, this is the inner function, this is the outer function here. But again, I want to know. So when I look down at my tachometer that says how fast my engine is going, I want to know how fast this is going. So in other words, I want to know what is dy dx? But I have this intermediate step here, right? So it's this other function, this g function is in the way. You know, u is in the way between my x and my y. So how do I get that? Well, dy dx is going to equal dy du you know, how fast is y going relative to this, times how fast is this going relative to this. So it's dy du, du dx. Oh, and look at those that's kind of slick. Those cancel. So this makes sense in all sorts of ways. That how fast is this going relative to this is the same as how fast does this go relative to this times how fast does this go relative to this. So that equals, go back to my black here. No, in fact, I'm going to do this in blue. I know that du dx is going to be 2, and dy du is 2.5 on the red side. So this is 2.5. So that's going to equal, when all is said and done, this equals 5. So when I'm done with this, my my blender is going to be running 5 times as fast as the rate of change of my blender is 5 times, you know, the rate of change of my engine, right? So if I'm counting the turns on this, it's going to change 5 times as much as this. Well, let's take a look at it. I just happen to have a schematic of this. Let's see if I can find it. Oh, here we go. Oh, yeah, look at this. I just happened to stumble upon this Volkswagen technical service website. Where here X, right, because all Volkswagens have an X on the flywheel, has this big, 10 centimeter wheel, which is connected to this 5 centimeter U wheel for, what does that stand for again? Unterklimaanlage, air conditioning in German. And that attaches to the Y, because why would you not want to have a blender in your Volkswagen van? Now, right now, these two are not connected, but if I put a belt around there, I'm going to wait till this gets to the top. So notice this is at 589. We're about to hit 590, and this is at 377. So we don't have a nice clean ratio, so we'll have to take a change in this over a change in this. Ready? 1, 2, 3. Get this time. There we go. Okay, now they're connected with this belt. So this is at 590. This is still at 377. So let's watch as this one goes around. That one's already gone around once. And by the time this gets to 591, this one will have gotten to 379. So this went up by 2 and then this went up in 1. So a little change in U over a little change in X, right, is 2. That makes sense. Okay, so now let's do the same thing, but let's connect these two guys here. We'll connect the Unterklimaanlage to the blender. Right when that gets to the top, and see how good I can time this. All right, there we go. Now, holy cow, look at this guy go. This blender is really cruising. I'll be able to make a sweet smoothie with this blender. Oh, here comes my assistant. So here we have this one is going 2.5 times as fast as this one because it has a ratio of 2.5 to 1, right? So at the end of the day, when I'm trying to figure out how fast is this going relative to this, it has to be the derivative, right? The relative rates of change to this times the relative rates of change to this. And so if I reveal that, what does it do? Oh, sure enough, it's 5. Right? It seems really obvious, but these two aren't connected directly. This is a function of this. This is a function of this. So they're nested functions, right? Okay. Now that may seem pretty obvious. I hope it seems a little obvious. Because they're nice and linear. Let's go back to the notes here. They're these nice linear functions. The derivatives are just constants, and we multiply the constants, and that's fine. Right. What if it's not so obvious? Let's do one where it's, this is the second page. Where's my third page? Oh, yeah, over there. So, what if it is not so obvious? Okay. What if we have something like y equals e to the x squared, right? What about this? And so what is dy, dy dx? What's that going to be, right? Well, what do we have? We really do have two nested functions. We've got e to the something, right? And so I like to put these in a blue box up here. So this is e to the something, right? But then, so I know that the derivative of y with respect to this thing will be dy dx equals the change in y relative to however my blue box changes, right, times the derivative of my blue box with respect to dy dx, right? Because this y depends on the e to the blue box, and then the blue box depends on x, right? So there's two things going on in between. The blue box is my intermediate function. My inner function, it's a function inside of a function. So if we write this out, dy dx equals, let's see, d blue box, right? Well, that's easy. E to the whatever stays to e to the whatever. That just stays to the e to the blue box, which is nice. But then I have to remember to multiply by the derivative of my inner function times, let's do that, blue box prime, right? Blue box prime. So when we do this, we don't mess with this. The blue box remains the blue box. That remains x squared. But the derivative of the blue box, of course, becomes 2x, right? So this whole thing, when we're done, typically we write the 2x first. This becomes 2x e to the x squared. So the derivative of this thing, there's a function inside of a function. We have to be sure to multiply it by this extra factor. Right? A little more complicated example. Let's look at this one. Another example, y equals, let's say, the tangent of e to the 3x. Wow. All right, so we've got actually three functions here. We've got our blue box, right, which is our little inner function here. But that's really our part of a bigger function, which is e to the 3x. Let's make an orange box, which finally is inside this tangent function. So y depends on the tangent of the orange box, right? The orange box depends on the exponential of the blue box. So we've got three functions inside of a function. A function, blue function, inside of an orange function, inside of the original y function. All right, well, how is this going to work? So we have to say dy dx, right? So y is a function of this, which is a function of this, which finally gets down to the x. Is going to be the derivative of this thing. So it's the derivative of tangent is secant squared of my orange box. Right? That's just how the trig one works. Times the derivative of this, which is just e to the blue box. Right? But that doesn't change either. Finally, times the blue box prime, which is blue box prime. Okay, so how does that thing finally look? That's going to equal secant squared of whatever was in here, e to the 3x, times the derivative of what was in here. Well, that's e to the 3x, because that doesn't change, times the blue box prime, which is, the blue box is 3x, so that's just times 3. So when I'm all done with this, I've got these extra factors in there. My orange thing showed up because this is orange box prime, and this is blue box prime down here. Right, so we've got I work from the outside in. I'm going to make a note of that. Work from the outside in. Now my heat is starting up. There's going to be a lot of background noise. Sorry about that. I hope it's not too loud for you guys. So this is my outermost function is tangent, so the derivative of tangent is secant squared. Everything here stays the same. The next function is exponential. Well, exponential, right, e to the 3x, is e to the 3x, times the derivative of whatever this innermost function was, which is 3. And a cleaner way to write this would be 3 e to the 3x secant squared of e to the 3x. All right, and that's our final answer. That is dy dx. Okay, now, one more kind of important one that I want to take a look at is, well, okay, so maybe you believe me. Maybe you're one of these teachers, or one of these students says, well, my teacher says to multiply by the derivative of the function, blah, 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 I trust you. You know, and again, I really hope you don't trust me. Don't believe me just because I say this stuff. Let's take a look at what actually happens. Let's look at one more. Y equals sine squared of x. Now this is a really confusing one because this notation is very confusing. So this really means y equals the sine of x. This is not multiplication, it's the sine of x. This whole quantity squared. Right, that's what sine squared of x, or the sine of x squared, sine squared of x, is sine of x quantity squared. Right? Oh, once again, a function inside of a function. The inner function is sine of x, the outer function is this thing squared. So we can say that y equals this thing, or so let's just say dy dx equals just the derivative of the squared function, right? 2 times the sine of x, and you reduce the power to the 1, so that's 1. But we have to remember to multiply by, since the sine of x depends on x itself, we have to multiply by the derivative of this, which is, derivative of sine is cosine of x, right? It's got to be this way. Let's take a look at that. So here I've got some plots ready to go. F of x equals sine squared of x. Let's take a look. What the heck? That's, oh yeah, right. Because you're expecting a sine wave to go up and down, up and down, up and down. But when we square it, everything becomes positive. So it winds up looking like this, right? The period becomes, well, pi instead of 2 pi. Let's expand this a little bit. So make this just a little bit longer, a little easier to read. So here we go. Here's the normal 2 pi, but since we're squaring everything, it looks like this. Right? Now, if we go back here, we said, well, we didn't, chain rule, whatever, not that important, so it's just going to be 2 times the sine of x, right? Power rule. So if it just becomes 2 times the sine of x, let's include this one. Right? Now, does this work out? Is the red one, in fact, the slope of the black one? I made it red because it's wrong. Well, here the slope is positive, but the slope seems to be increasing, right? The slope is positive and increasing. It seems good so far. Now the slope starts decreasing until the slope is 0. All right, now, this is first derivative, second derivative, concavity, curving, blah, blah, blah. I know for sure the slope here is 0. The slope here is definitely not 0. I mean, the slope here is 0, but the value of the function, the red one should be the slope of the black one. Here I've got a slope of 2, right? It's saying my derivative is 2, and actually I know the slope is 0. So this is just not right. It's not just we forgot the chain rule. It's just flat out wrong. The slope here is 0, but my derivative says that the slope is 2. That's terrible. We get down here, and then the red one is 0, and the slope is 0. So okay, that's correct there. Wrong here, correct there, wrong there. So this has got a lot of problems. If we include the chain rule, right, we have to multiply by the derivative of our inner function. We have to multiply by the cosine of x. Well, let's plot this one now. let's get rid of this, plot the correct one. Does this match up, right? Convince yourself that this works. Pause it if you have to and take a look. Is this correct? Let's see, the slope is positive. Sure enough, the slope is positive and it's getting bigger. The slope is positive and it's getting bigger. But then let's see, the slope up here, it's kind of reached a maximum. The slope has reached a maximum. Yeah, this is about as steep as it gets. But then it starts to taper off a little bit. And by the time we get over here, the slope of my original function is 0. Oh, and sure enough, the slope drops all the way down to 0. Nice. The slope becomes negative. It starts going downhill. The slope is negative. Sure enough, the slope is negative. This is as low as the slope gets. It's as steep as it gets going down. The slope is as low as it gets. And then, let's see, we've got the slope kind of gets shallower and shallower, shallower, and the slope hits 0. Sure enough, the value of our slope, the value of the derivative hits 0 too. So this is correct. The red one is wrong. Pause it here, look at these, see if that makes sense, convince yourself that this is correct. All right, so that's all I have to say about the chain rule. Let's leave it on this one here, and hopefully this makes sense. If you have any questions, please ask about it, but this should give you a good head start as to the homework. Take care. See you on Tuesday.